Good morning, everyone. In the previous lecture, we have covered the problem of minimizing some objective function subject to equality constraints. And we have seen how to use the Lagrange method to solve this optimization problem. And the Lagrange method was based on first forming the Lagrangian, which is a function of the original optimization variables, plus the Lagrange multipliers. And the Lagrangian is composed of two parts. The first one is the original cost function. And then we have the weighted sum of the constraints in this form here. Okay? And there is actually one point which I want to make here, that sometimes we don't have the problem directly in this form. For instance, we could have a problem where we are maximizing some function, for instance f of x, and we might also have constraints which are not directly in this form. For instance, we might have constraints which are something like x1 less than x2 plus 5, for instance, okay? So always step number one before we can start using the Lagrange method is first to convert this optimization problem into the standard form. And the standard form is when we are minimizing the objective function and the constraints are always less than equal 0. Okay? So the translation here is rather easy. So when we are maximizing, we can flip the function and minimize the flipped function. That means equivalently we can minimize minus f of x, and then all constraints need to be converted into this standard form where we have less than or equal to, and we have 0 on the right hand side. Okay, so this is just to remind a very important step without which the Lagrange method would not work. Okay, so never forget to first bring the problem into minimization. Always convert the problem where we have 0 on the right hand side and we have less than or equal to as the comparison. Meaning that if we would consider the constraint, for instance, x2 larger than 0, then of course we have to convert it into minus x2 is smaller than, okay, let's put it in a non-zero number here. Then it would be, so we would multiply both sides by minus 1 to flip the inequality. So here we would have minus 1. Okay? So that's the translation that we need to do at the very beginning. Okay? And then what we have started at the end of the previous lecture was that these Lagrange multipliers, they actually not only allow us to solve the problem, to obtain the optimal solution, but those multipliers also have some economic interpretation about the change of the objective function when the right-hand side of the constraints, meaning this b here, which is a constant, when that constant changes by some delta here. And we have seen that if we have the Lagrange multipliers, which are associated to the problem where the right-hand side is just b, then these optimal Lagrange multipliers, they tell us what will happen to the objective function if we change the right-hand side of the constraints to b plus delta. And we have seen that the objective function changes by minus the value of the Lagrange multiplier multiplied by the value of the change of the right-hand side of constraints. Okay, so if the Lagrange multiplier is negative, this minus here makes the product positive. That means if we increase the right-hand side, the cost function will increase. Okay, if the Lagrange multiplier is positive, then if it is positive, then a positive change of the constraints actually decreases the value function. And therefore, the value of the Lagrange multipliers at optimum, they represent or relate to the sensitivity of the optimization problem with respect to changes in the right-hand side of the equality constraint. And just to illustrate this concept, this is the same example that we have covered the last time. So we are looking for the optimal composition of 3 heating fuels that our company would like to buy. And we have two equality constraints. The first one says how much heating power do we require, and the second one is how much of a volume do those fuels consume. Okay? And notice that we have two linearly independent constraints and we have three optimization variables. Okay? So there is still space for optimization, because if we would have three linearly independent constraints, then the solution would be uniquely determined by the constraints themselves. Okay? So we always, so in this case, basically, we have 1 degree of freedom to play this. Okay? And if we solve this problem using the Lagrange method by first forming the Lagrangian and then setting the gradient of the Lagrangian equal to 0, we obtain the following solution, meaning we purchase a little bit of coal. I mean, it's the cheapest fuel that we have, but it also has the smallest heating power generated by burning one amount of coal, and it also consumes the highest volume. Okay, so that's why coal is not so much preferred, and we are preferring the other fuels despite them being a little bit expensive. Okay, and these are the corresponding Lagrange multipliers. So what kind of information do they convey? What do they say, actually? The first one is negative. So it basically says that if we would increase the desired heating power by some delta, okay, so not 200, but say 210 is the required heating power, what will happen to the cost function? Okay? And we know that the change is proportional to the minus of this number times the change, okay? So minus cancels with this minus, so it's just this 680 multiplied by the change, okay? So if we require more heating power, since our cost is the amount of money that we pay, and minus times minus this number plus times a positive change implies that the value of the cost increases. Okay, so if we require more heating power, we will have to pay more to buy that heating power. Okay. However, this second Lagrange multiplier is positive, and remember the change of the cost function is proportional to minus the value of the Lagrange multiplier. That means that if we allow to store more volume than 100, say 120 volumetric units, that would actually decrease our cost. Why? Because then we would actually buy more of the coal because we have more storage available. So we can actually buy more coal since that consumes more space, but it's cheaper. Okay? So if we change only the second constraint to say 110, the cost will go down. Of course, we can also consider like the negative change of the constraint. So if we restrict our volume, say from 100 to 90, our cost would go up because the change would be negative, that delta would be negative. Okay? And if we decrease the heating power, which is required, then we drive the cost down because, again, the delta is negative. Okay? So that's the general kind of the idea of the economic interpretation of Lagrange multipliers. And actually, once we solve the problem once, we can analyze the sensitivity of the optimization problem in some close neighborhood of the original problem. Of course, if somebody would change the right-hand side of the constraints not by small amount, but say from 200 to 2000, that's a large change. Those Lagrange multipliers, I mean the extrapolation based on the Lagrange multipliers would no longer be meaningful. Okay? So sensitivity is about analyzing what happens if we slightly perturb the problem. Okay? So this sensitivity analysis then allows us to answer very interesting questions. So how will the purchase price change if the required heating power decreases by 20%? So what do you think? I mean, will the purchase cost go up or down if the 200 here changes to 160? So what will happen to the cost?
It will go down.
It will go down because here we have minus times minus, and actually also the delta is negative. Okay. Then we can say how will the purchase price change if both of these actually change. Okay. So what if both the heating power goes down by 10% and also the volume goes down by 10%? Now this is less obvious. What happens? We know that the change will have like opposite directions. One of them will increase the cost, that's this one, and the other one will decrease the cost when the right-hand side goes down. Okay? So the delta that we are analyzing now is negative. Okay? But what if both go down? Not just one of them, but both.
The price will decrease.
Why?
Because the required heating power has a greater absolute value lambda.
Of the Lagrange multiplier, yes. So it's essentially about the ratio of the absolute values of these terms here. So essentially it says that the problem is more sensitive to changes in the first constraint and less sensitive to changes in the second constraint. Okay? And I mean, then we can interpret it like, okay, so we want the price to stay constant or roughly constant, and we need to increase the heating power by 10%. We know increasing the heating power is more costly, incurs more cost. So we can compensate it by decreasing the volume. Okay? And again, by essentially looking at the ratio between these two numbers, we can say that if we change the heating power by 10%, then roughly by 30% we should decrease the volumetric constraint in order for the cost to stay like kind of constant. Okay? So that's the kind of information which the Lagrange multipliers provide us. And I would like to conclude the explanation of the Lagrange method by two things. The first one is one very standard application of the Lagrange method to a special type of problems which occur very frequently in practice. And these kind of problems are represented by the so-called equality constraint quadratic programs. So essentially the problem we are looking at has a quadratic cost function. We assume that the matrix P is positive definite, therefore the problem is convex. And we have equality constraint. How would we apply the Lagrange method to obtain the optimal solution here? So we would need to write down the Lagrangian. So we have the problem of minimizing x transpose px plus q transpose x plus r, and we have linear equality constraints. So step number one, forming the Lagrangian. What will be the Lagrangian here? So that's the original cost function plus the weighted sum of the residuals by putting the b on the left-hand side. Okay? Now we have to form the gradient of the Lagrangian, and at the optimum the gradient has to be equal to 0. So what is the gradient of Lagrangian with respect to x? So what is the derivative of this term with respect to x? And we are assuming that P is positive definite and it's also symmetric matrix. Okay? So then this derivative here, remember those rules that I put here, if we have something like z transpose qz, derivative with respect to z is q plus q transpose times z. Okay? The derivative of some q transpose z with respect to z is just q. Okay? So here it's actually this first rule, so it's P plus P transpose. But since we are assuming that P is a symmetric matrix, it's just 2px. Then here, that's actually this rule, so that's plus q. R doesn't depend on x, so that goes away. And here we have the product, me transpose to ax, and we have to make a derivative with respect to x. So it's the same thing, so we have to make a transpose of this term here. Okay, so that's plus A transpose me, and that in the optimum, so for optimal x and optimal me, it should be equal to 0. And we also need the gradient with respect to me, and that's what? So this term doesn't depend on me, neither does this one, neither that one. This one does depend on me, okay, and the derivative is just the bracket itself. Okay, so ax minus b, and that must be equal to 0 at the optimum. Okay? And now what we would like to do is to find the optimal x and optimal Lagrange multipliers. And actually, if you look here, we notice that x and me, they enter this system of linear equations, well, the system of equations in a linear fashion. Okay, so these are all linear equalities in x and me. And we know how to solve the problem, so we just make the matrix formulation where we solve for x star and me star essentially from minus q, and here we would have b. Okay, so that's how we solve this problem. And actually, this matrix or this system of equations here, it's very frequently used, and it's called the Karushkun-Tucker system. Okay? And we will use it for something else in a second. Okay? So this basically says that if we have a quadratic optimization problem with equality constraints, we can obtain the optimal solution just by solving a system of linear equations. Okay? And we know that to solve this system of linear equations, basically we have to invert this matrix. Now, this matrix in general does not have to be invertible. Okay? It all depends whether, for instance, these constraints here or the rows of this matrix here, if they are linearly independent, and if P is a positive definite matrix, then that matrix inverse exists. If, for instance, P would not be positive definite, or if A would contain linearly dependent rows, this matrix here would not be invertible, or wouldn't need to be invertible. Okay? But in nice cases, we can obtain the solution just by solving a system of linear equations. Okay? The question now is, how do we apply the Lagrange method if this objective function here is not quadratic, but it is something more general, like some arbitrary convex nonlinear function, like this. Okay? How do we solve this problem? Bless you. Okay? One option is to solve the problem analytically. Okay? We would form the Lagrangian, which is f of x plus me transpose times ax minus b. And we would make the gradient of this, which is the gradient of f of x plus the, okay, so that's the gradient with respect to x. So here it's a transpose me. And the gradient with respect to me is just ax minus b. Okay? And at the optimum, this has to be equal to 0. Well, the problem now is that if the function, the objective function is nonlinear, probably also the gradient is nonlinear. Okay? And then we end up with nonlinear inequalities. Equalities. Okay? So those equalities could be now like something like sine of x1 to the power of x2, okay, plus A transpose me, and that should be equal to 0. How do we solve this equation? There isn't probably, or very often, there is no analytical expression for a solution to nonlinear equations like this. Okay? So what happens if the gradient is nonlinear? Here in the quadratic case, the gradient was linear. That was the nice thing. So take a look here. So our objective function is x transpose px plus q transpose x plus r. What is the gradient of this function? Well, that's just px plus q. Okay, that's the gradient. And we see that the gradient is linear in x, because p and q are just constants, okay? So here we have a linear gradient, but in general the gradient can be nonlinear. So what do we do then? How do we solve the problem? Well, it's the same problem that we had in the unconstrained optimization. Also in the unconstrained optimization, we started with analytic solutions, and we said, if that works, if the gradient is linear, that's an easy problem. But we can also find the optimum if the gradient is nonlinear. Do you remember how did we do that? How do we solve an unconstrained optimization problem whose gradient is nonlinear? And there were at least two principal ways. Well, the first one was gradient-free methods. Random search, simulated annealing, extremum seeking, whatever. But those methods didn't even assume that we know the gradient. Here we do know the gradient, but it's nonlinear. So we use gradient-based methods, and we know that the most efficient one, with respect to the number of iterations, is actually the Newton method. Okay, and we can apply the Newton method also to equality constraints, and there are actually two types of a Newton method here. One of them is called the feasible start Newton method, and the name is due to the fact that this method assumes that we start from some feasible initial condition. Okay? That condition has to satisfy these equality constraints. Any ideas how to find some suitable starting point which satisfies constraints? I mean, that's the particular solution of the system of equations. That's what we have covered in the previous lectures, right? So we just do the pseudo-inverse of A and we multiply it by B. And that's some particular solution. So actually finding some solution, at least in theory, is easy. Okay? So let's assume that we have found some particular starting point X. Now, how does the Newton method work? And any gradient descent method work? Well, first, we determine the direction in which we want to go. We determine how far we are going in that direction. And we obtain the next iterate as the previous iteration plus t times that direction here. And we repeat until convergence. Now, the question is how to find this delta here. What we have seen in the unconstrained optimization is that this delta here was given as minus the Hessian times the gradient of the function, right? But this was kind of the optimal direction without constraints. It is not necessarily the best direction when constraints are present in the optimization problem. So how can we actually find the best possible direction? Actually, the problem we are looking at is, so that's the original problem that we want to solve. And the new problem that we are looking at is the following. We are already at some x. We can call it some x0. And we are asking ourselves, how much should I add to the current point such that I minimize, I decrease the function such that I stay feasible? What does that mean? For x0, we were already feasible because we are assuming that we have some initial starting point which satisfies constraint. What do we require to stay feasible after moving into the delta direction? Well, we do require that A times x0 plus delta is equal to B. Now, what does this really mean? It means, let's expand that, that's AX0 plus A times delta is equal to B, right? But we are assuming that this AX0 is equal to B, right? So what does that imply? For this to hold, A times delta must be equal to 0, right? For the next point, because this is kind of the next point, let's call it x1. For this point to stay feasible, meaning to still respect constraints, okay? So this is now the problem that we would like to solve. We would like to find the delta such that we minimize this function subject to these constraints, okay? So we have kind of changed the problem. Before, we were optimizing with respect to x. Now, if we want to optimize with respect to x using the Newton method, it means that at every iteration, we have to find the best possible step direction and the step size such that we converge to the optimum. And that can be achieved by solving a new problem. Now, how do we solve this new problem? How would you find the value of delta which minimizes this objective function subject to these constraints? What kind of a problem is that? It's an equality constraint optimization problem. How do we solve it using the Lagrange method? We form the Lagrangian, okay? So let's form the Lagrangian of this new problem. So the optimization variables are delta, and we would need some Lagrange multipliers, okay? So that's the original cost function plus mu transpose times A times delta, okay? Notice that the constraints are already in the standard form. And what we add multiplied by mu into the Lagrangian are just the left-hand sides of the constraints in the normal form or in the standard form, okay? Okay, so how do we solve that? Well, we compute the gradient, right? So what is the gradient of this function here? What is the gradient of the Lagrangian with respect to x? Well, that's the gradient, sorry, not x, but delta. That's the gradient of this function plus the gradient of this with respect to delta, that's A transpose mu. And we know that at the optimum this must be equal to 0. And then we also need the gradient, let me put it like this. Then we need the gradient of the Lagrangian with respect to mu, and that's just A times delta. And again, at the optimum this must be equal to 0. Okay? But, I mean, what did we achieve? We started by assuming that we don't want to use the Lagrange method because the gradient is nonlinear. It was nonlinear in x. I mean, it will be nonlinear in delta as well, so we didn't help ourselves too much. Well, except that since we are now using iterations, maybe we don't require the exact gradient here. Maybe we just require an approximation of the gradient, because by using iterations we will improve that approximation. Okay? So let me now give you a question. Imagine you have a function like this. Let's call the function, for instance, g of x. This is the current point, x, for which I know what is the value of the function. I can just measure the value. Okay? I'm asking, what will be roughly the value of the function at a point x plus delta? Give me some mathematical relation which at least roughly tells me what is the value of g at this point. So this is g at x. This is g at x plus delta. I would like to know at least an approximate value of this of the function at this new point. What I can measure, okay, I will give you a hint. What I can measure is not only the value of the function at point x, but also the value of the derivative of the function at that point. So in other words, I also know this derivative here. Okay, it must be a straight line, I apologize, it must be something like this. What is now, roughly, what is the approximation of the value of g at this point?
Now we know the length and direction.
The length is delta. So this delta. How do I know this value? Well, roughly, I mean, if the delta would be small, essentially that's the argument for how linearization works. Essentially what we are doing here, we are linearizing the g function, which can be anything. It can be any nonlinear function. I mean, here it could be something like this and so on. But at least locally, we can make a linearization of that function. Okay? And what I'm asking is, what is roughly this value if I know the value here and I know the derivative? Well, since I'm looking for an approximate value, I can at least give this value here. What is the value of the function at this point, roughly? Well, what is, in other words, what is the linearization of g of x around some x? That's the value at some linearization point of the function plus what? Linearization. How does linearization of a function work? So we take the derivative of g at x and times the delta. Right? This is an approximation of this value by the red value. Okay? And that's exactly what we will do here. We would like to approximate the value of the gradient at some new point. In other words, our function is the gradient of f. Okay, so it should be like this. An approximate value of the function g at time, at point x plus delta is the value of the function at point x plus the derivative of the function at that point multiplied by the delta that we are considering. Okay? Now, what if the function now is this one? So the function is already a derivative. What would then be this linearization of a derivative around x? Let's use the same procedure. So now g is the gradient of f. Okay? So then the linearization would be the function itself at that point, so the gradient of f at x plus the derivative of the function. Now the function is already a derivative. So what is the gradient is the first derivative. Here we have to consider another derivative. So what do we obtain? The second derivative, or the Hessian. Okay? So here we have the Hessian of f at point x multiplied by delta. Okay? That's the local approximation of the gradient. What is now the beauty of this? The beauty is that we have taken the delta out of the nonlinear function. And we are only assuming some point-wise measurements of the functions. So I don't care how complex f is, because I'm only taking the value of the gradient and the value of the Hessian at some particular point. So I can just evaluate the function at that point during the iteration. So this is no longer a function, it's just a function value. Okay? So I don't care that it's nonlinear. At the end, it will just be a constant. And we have taken the delta outside. So here we have one constant plus another constant times delta. So this is now linear in delta. Okay? So let us now use or replace this gradient here by its approximation. Essentially what we are doing here is we are taking the first order Taylor expansion of that function. Okay? So when we do that, what do we obtain? So we just make a substitution. Okay? So instead of the gradient at point x plus delta, we take the Taylor expansion here. So the Taylor expansion is the gradient of f at point x. Remember, x is a constant. It is not an optimized variable. We are at some iteration, say at the first iteration. What we said was select some initial point, so select the x. X is a constant. This is just the value of the gradient at that point, so it's a constant as well. Then we have the Hessian, again at this point. So again, this is a constant, multiplied by delta. So we have taken out the delta from the nonlinearity. And now we have the, so this is the red part. So that's the local linearization of the otherwise nonlinear gradient, plus A transpose times me. So the rest we are just repeating as it was. And at the optimum, where there are stars attached to the optimization variables, the gradient has to be 0. How do we now find the optimal delta and optimal mean? I mean, what's nice here? The nice thing is, me and delta enter linearly into these equalities. Again, these are just constants. The gradient at the iteration and the Hessian are constants. Okay? So we can convert this problem into this matrix form where we will have a matrix multiplied by the optimal delta and the optimal me, and we will have some right-hand side. So in the first equation, what multiplies delta star is just the Hessian of the function, evaluated at the current iteration. Me transpose is multiplied by A transposed. In the second equation, delta optimal is multiplied by A, and me optimal is multiplied by some zero matrix. Okay? And we still have some constant terms that need to be put to the right-hand side. Specifically, the constant term is this one. Okay? So here we have minus the gradient evaluated at x, and here we have a zero vector. Okay? So this is why solving this system of linear equations provides the best possible direction in which we should update the iterations. In other words, this feasible start Newton method can be used to find an optimum of arbitrary nonlinear functions, even in cases where the gradient is nonlinear. Of course, if the function to be minimized here is convex, then what type of an optimum do we find? Do we find the global optimum or just the local optimum? The global one, because the function only has one optimum. If the function would not be convex, then depending on the choice of the initial condition, we can either end up in a global optimum, but in general terms, we can only end up with or in a local optimum. Okay? So that's why we usually, or that's why we like to consider convex functions, because then we don't care what type of optimum we have found. We know it's the global one. If the function is not convex, no such guarantee is given. Okay? So this is how the feasible start Newton method works if we have equality constraints. The principle was that we analyze what happens to the problem when we kind of change it by delta. Then we look for the best possible delta by solving essentially equality constraint optimization, where we approximate the nonlinear gradient by taking its first order Taylor expansion. Okay, so we are analyzing what happens locally to the function when we change the point which might be optimal. Okay, now a tricky question. What do you think? In how many iterations will this feasible start Newton method converge if this value function here is quadratic? If you remember, we had something similar before. The answer was 1 in which case?
And the cross function was quadratic.
Sure, but there was also another difference. Without the presence of constraints. Okay? If there were no constraints, then yes, the Newton method with the step length equal to 1 converges in exactly one iteration. We have seen the proof. Now, what if we add constraints? It might be surprising to some that still the Newton method, the feasible start Newton method, still converges in exactly one iteration, even if we have constraints. Now, you should never trust me just saying something. There must be a proof saying this. Okay? And the proof is the following one. Imagine that it takes exactly one iteration. What this means is that if I start with an arbitrary x, then the delta that we find by solving this system of equations is such that this term here is exactly the optimal point. Okay? That's the way how we can show that in exactly one iteration with t equal to 1, this point is the optimum regardless of where we start from. Regardless of the choice of the starting point, if the function to be minimized is convex quadratic function, this delta resulting from this system of equations will exactly give the global optimum. Now why? That's why I have put also this one here. Can you notice some similarities between that problem? Actually, what we are saying is that this first term is the Hessian of the cost function. Now the cost function is quadratic. What is the Hessian of this function? It's exactly this term here, 2p. So 2p is exactly the Hessian that we have here. What is the gradient of the objective function? Right? So actually, these two problems, they are the same. Okay? It's just that here we are not analyzing, here we are analyzing x, which has to satisfy ax is equal to b. In this case, we are only analyzing the delta, so that's why now here we don't have a b as it was there, but we have 0, and that's coming from essentially from here. Okay? Because x has to satisfy ax is equal to b. Delta only has to satisfy a times delta is equal to 0. So essentially, if you do this same procedure, starting from a quadratic function, and we can also do that. Okay, so what we are saying is, and then I can really wipe this one, maybe even better way of showing that is, let's assume that the problem now is the following. We would like to find the delta such that starting from some arbitrary initial condition, which is feasible, this problem here we find the minimum of it such that a times x plus delta is equal to b. Okay? Since we are assuming that this initial point satisfies constraints, we can immediately simplify these constraints into a times delta is equal to 0. Right? What is now the Lagrangian of this new problem? Well, that's this function here. So it would be, the Lagrangian is a function of delta. These are now the new optimization variables and the Lagrange multipliers. So that's just this guy here. Let me expand it immediately. So that's something like this. 2 times x transpose p times delta plus delta transpose p delta plus q transpose x plus q transpose delta plus r plus me times a times delta. Now we take the gradient of the Lagrangian. The gradient with respect to delta is what? This one doesn't depend on delta.